Table 220.19 is used to determine the demand factor for multiple appliances. The demand factor is a multiplier used to calculate the actual load demand on the electrical system. The demand factor will reduce the total load size to account for the non-simultaneous operation of all devices. For two electric ranges rated at 11.2 kilowatts each, Table 220.19 indicates a demand factor of 1.25 for the first range plus 0.80 for the second range, totaling 2.5. To calculate the actual load demand, multiply the demand factor by the total connected load. In this instance, it would be 2.5 times 2 times 11.2 kilowatts, which equals 47.1 kilowatts. To determine the minimum wire size, you need the actual load demand and the voltage of the electrical system. Use the formula wire size in kc mil equals actual load demand in kilowatts times 1000 divided by the voltage times the allowable current density. For a 240 volt system and an allowable current density of 100 amps per kc mil as per table 310.15. B16, the wire size in kc mil equals 47.1 kilowatts times 1000 divided by 240 volts times 100 amps per kc mil, resulting in 196.3 kc mil. Therefore, you would need a number 3/0 American wire gauge copper wire to supply both electric ranges. Let's go over this again. Firstly, the demand factor from Table 220.19 for the first range is 1.25. Secondly, the demand factor from Table 220.19 for the second range is 0.80. Thirdly, the total demand factor is the sum of the individual demand factors, which equals 2.5. Fourthly, the total connected load is 2 times 11.2 kilowatts, which is 22.4 kilowatts. Fifthly, the actual load demand is calculated by multiplying the total demand factor, which is 2.5, by the total connected load, which is 22.4 kilowatts. This results in 47.1 kilowatts. Sixthly, the voltage of the electrical system is 240 volts. Seventhly, the allowable current density from Table 310.15. B16 is 100 amps per kc mil. Eighthly, we can determine the wire size by dividing the actual load demand, which is 47.1 kilowatts, times 1000, by the voltage, which is 240 volts, times the allowable current density, which is 100 amps per kc mil. This results in 196.3 kc mil. Finally, based on the calculated kc mil, you would need a number 3/0 American wire gauge copper wire. This is just an example of using Table 220.19 to find the demand factor and the wire size. Now let's talk about some other considerations. The numbers used in this calculation are for example only and might not be applicable to your specific jurisdiction. Always consult with a qualified electrician to perform electrical work. Electrical work can be dangerous and should only be performed by someone with the proper training and experience. It is important to understand the purpose of the demand factor. It allows for the reduction in the calculated load based on the understanding that not all electrical appliances and equipment will be operating at their maximum load all of the time. This allows for the correct sizing of electrical equipment and wiring without oversizing. In the example, we used an allowable current density of 100 amps per kc mil based on Table 310.15. B16. This is the ampacity of conductors rated 60 degrees Celsius through 90 degrees Celsius, not more than 3 current-carrying conductors in a raceway or cable or earth. Always refer to the NEC or your local code to understand the specific requirements for the allowable current density based on the type of conductor, the insulation type, the ambient temperature, and the number of current-carrying conductors. The calculated wire size is based on copper conductors. If aluminum conductors are to be used, the calculation will change. Aluminum conductors have a lower conductivity than copper conductors. This means for the same amount of current, a larger size aluminum conductor will be needed than a copper conductor. The calculation only considers the ampacity requirements for the wire size. You also need to consider voltage drop. Voltage drop is the reduction in voltage that occurs as electricity flows through a wire. Excessive voltage drop can cause equipment to malfunction. In order to minimize voltage drop, the wire size needs to be increased. The amount of voltage drop that is acceptable depends on the type of equipment being supplied. It is always a good idea to minimize the voltage drop as much as possible. The calculation does not take into account any future expansion. If there is a possibility of adding additional load in the future, the wire size should be increased to accommodate the additional load. It is always a good idea to oversize the wire slightly to allow for future expansion. The calculation also does not take into account any dirting factors. Dirting factors are factors that reduce the ampacity of a wire. Some common dirting factors are ambient temperature and the number of current carrying conductors in a raceway or cable. If there are any dirting factors, the wire size must be increased to compensate for the dirting factors. The calculation assumes that the electrical system is properly grounded. Grounding is the process of connecting the electrical system to the earth. Grounding protects people from electrical shock. The calculation does not take into account the length of the wire run. The longer the wire run, the greater the voltage drop. If the wire run is long, the wire size may need to be increased to compensate for the voltage drop. The calculation also does not take into account the type of conduit or cable being used. The type of conduit or cable can affect the ampacity of the wire. The calculation also assumes that the electrical system is properly protected by circuit breakers or fuses. Circuit breakers and fuses protect the electrical system from overloads and short circuits. It is also important to understand the specific requirements of Table 220.19. This table is specifically for household cooking appliances. The notes at the bottom of the table provide additional details and exceptions. For example, Note 1 states that over 12 kilowatts through 27 kilowatts increase the maximum demand by 5% for each kilowatt or major fraction thereof that the maximum demand of ranges of the rating exceeds 12 kilowatts. Note 2 provides an exception for ranges all of the same rating. Note 3 applies to wall-mounted ovens and counter-mounted cooking units. Table 220.19 is just one part of the NEC. There are many other tables and sections that need to be considered when designing an electrical system. Always refer to the latest edition of the NEC and your local codes. Here are some additional tips for calculating wire size. Firstly, always use the correct voltage for the calculation. Secondly, always use the correct allowable current density for the type of wire being used. Thirdly, always consider voltage drop. Fourthly, always consider future expansion. Fifthly, always consider dirting factors. Sixthly, always make sure that the electrical system is properly grounded. Seventhly, always make sure that the electrical system is properly protected by circuit breakers or fuses. Eighthly, always consult with a qualified electrician to perform electrical work. Ninthly, understand the purpose of the demand factor to avoid oversizing equipment. Tenthly, consider that aluminum conductors require larger sizes compared to copper for the same current. The actual load demand calculation is critical for determining the appropriate wire size to ensure safe and efficient operation of electrical appliances like electric ranges. The 47.1 kilowatts figure derived from applying the demand factor to the total connected load represents the maximum anticipated power draw under normal operating conditions. This value is then used in conjunction with the system voltage, which is 240 volts, and the allowable current density from Table 310.15. B16 to calculate the required wire size. Understanding the NEC requirements and application of demand factors ensures compliance and safety in electrical installations. When calculating the wire size, the kcmil value of 196.3 kcmil indicates the cross-sectional area of the conductor needed to safely carry the calculated load. The standard wire gauge that corresponds to this kcmil value is a number 3/0 American wire gauge copper wire. This wire size is selected to ensure that the conductor can handle the current without overheating, which could lead to insulation damage or even a fire. In this scenario, remember that the ambient temperature and the number of current carrying conductors play a crucial role in determining the final wire size. High temperatures and multiple conductors in a raceway can reduce the ampacity of the wire, necessitating a larger conductor to maintain safety and efficiency. Voltage drop considerations are also paramount, especially over longer distances, to ensure that the electric ranges receive adequate voltage for optimal performance. Always prioritize safety and compliance with electrical codes to prevent hazards and ensure long-term reliability of the electrical system. The NEC provides guidelines and tables like 220.19 and 310.15, the 16th, to assist in these calculations. Remember, it's essential to stay updated with the latest edition of the NEC and local electrical codes, as requirements can change.